Prabhanjan. I'm in Vinod's crypto group, so I'll be taking your class today. I want to apologize for making guys sit here instead of enjoying the sun outside. I'll try to make it as fun as possible. Okay, so the goal for today's talk is going from semi-honest secure MPC to malicious secure MPC. You guys must already be familiar with what semi-honest security means, right? So, and if I'm correct, you guys aren't familiar with what malicious security is. Am I right? Okay. So, let me start by explaining what malicious security is, and we will see how to start from a MPC protocol that is secure in the semi-honest setting, and we will show how to go to malicious security setting. And as intermediate tools, we will need some cryptography primitives, and that I will introduce whenever it's necessary. Okay. Okay. So feel free to ask any questions if you have doubts. Okay. So let me briefly recall what semi-honest security means, and then I will go to malicious security. Okay. So in the semi-honest setting, what can the adversary do? Right. So the adversary is given. The adversary gets some inputs, right? And he has randomness, right? He can observe what is going on in the protocol, but beyond that, what he cannot do is change his inputs and randomness. So whatever inputs and randomness he gets from the environment, he has to use them throughout the protocol. Okay? Has to use okay. And what he cannot do is deviate from the protocol. So he has to follow every instruction of the protocol. So this is going to be informal. I'm not giving you the formal semi-honest security definition because you guys are already familiar with. Has to follow. And what he cannot do is abort the protocol, right? So he has to execute the protocol, and at any point of time he cannot abort. Right? So. So these are the things he has to comply by. But this seems very artificial, right? Why should we expect the adversary to actually follow the protocol? Why should we expect the adversary to use the same inputs and randomness throughout the protocol? Why should we expect him to not abort? Right? This is not how real-world adversaries work. So in order to capture real-world adversaries, we define the notion of malicious security. Okay? So let me first give the intuitive definition of malicious adversaries, and then I will give the formal definition. Okay. Malicious. Well, if something is not clear here, please let me know. Okay? My handwriting is not too good. So in this case, so an adversary need not use the same inputs and randomness he obtained from the environment. In fact, he could potentially change his inputs and randomness as the protocol progresses. Change inputs, randomness at any time. Okay, so, and what he could also do is not follow the instructions of the protocol. So if the protocol says, add these two elements, he can multiply these two elements. Right? So he can essentially deviate from the protocol. And finally, he can actually abort at any point of time in the protocol. For instance, he can actually obtain the outputs of the computation, and even before the honest parties obtain the output, he can abort the computation. He can abort the protocol. Okay. In such a case, only the malicious adversaries receive the output. The honest parties don't receive any output. So is this intuitive notion clear? Yeah. So how do we capture such adversaries, and how do we formalize security against such adversaries? This can be done by using the real world, ideal world paradigm. And I think this was introduced in all the previous classes, right? Okay, so let me give you the formal definition. Okay. So first, let me give the definition diagrammatically, and then I will state it in words. Okay. So here you have the real world, and you have that real world. So in the real world, there are many parties. Okay, for any n greater than or equal to 2, and the adversary can actually corrupt any strict subset of these parties. Right? So he can corrupt this party. He can also corrupt this party. So there is no restriction. I should point out that here also there are different models. In one model, the adversary can actually corrupt every party except one party. This is called all but one corruptions. All but one corruptions. And there's also other models which are weaker, where the adversary can corrupt something like less than half of the number of parties. In other words, we have honest majority. Yeah. So the BGW protocol, which you saw in the last class, is actually in this setting, right? I mean, in that case, the adversary can only corrupt a fraction of parties that is less than half. Okay, so we are going to deal with this. Okay, so I'm only interested in the setting where the adversary can corrupt all the parties except one. So this is what he can do in the real world, right? So, and as I said, he can essentially change his inputs, deviate from the protocol about any point of time and so on. So what do we want to, how do we capture this in the ideal world, right? So in the ideal world, we have this trusted party, right, who has the function f that is being computed. Okay, he is a trusted party, he has the function f that is computed. Right? And there are all these parties that don't communicate with each other, but instead only communicate with the trusted party. Okay? So they send their inputs, let's say they have x1, x2, xn, and they correspondingly receive the output. So for now, let's deal with the simple setting where all the parties receive the same output. Okay? So we can also look at the setting where each party receives different outputs, but that's not really relevant for this discussion. Okay, so we want to capture these adversaries in the ideal model, right? So here, again, we have these adversaries, right, who essentially just talk to the trusted party. So we want to argue that if for every set of adversaries here, there correspondingly exists a simulator, So we want to capture that for every set of adversaries there is a simulator. I'm going to denote this by sim. Who has access to these parties, the code of these parties. Okay? So he has access to E2. And he can send these inputs x2 to x. Okay? Okay. So for every set of adversaries, there exists a simulator such that the view of the parties here, right? The joint view of all the parties here is indistinguishable from the output of the simulator, along with the outputs of the honest parties here. Okay. Okay, does it make sense? So what is the output of this? The output of this is the output of the honest parties plus the views of all the adversaries here. And what is the output here? Here also is the view of the honest parties. Here there is only one honest party, but you can envision more honest parties. So the outputs of honest parties along with the view of the simulator. Okay. The view of the simulator is essentially the same as the output of the simulator. Does it make sense? Okay, so let me give the formal definition. Okay, so the definition is consider an n-party functionality f okay. A protocol phi for f is secure against malicious adversaries if the following holds: for every adversary, right, which can corrupt a strict subset of the parties, there exists, all these are probabilistic polynomial time. You can also consider unbounded adversaries, but in my talk I'm only going to consider computationally bounded adversaries. There exists a probabilistic polynomial time simulator, denoted by sim, such that the following two distributions are indistinguishable. Okay? And I'm only going to consider computational indistinguishability. So in the left we have something that corresponds to the real world, which is the input of the honest party. Here I'm only considering corruption of P1, but as I said, you can consider a more general definition. X1, comma, view of the adversary. Okay. Oh, sorry, I should say not just. I should say. I didn't mean to say X1 here. I meant the output of P1, which is output from the view of the adversary. Okay, is indistinguishable from, again, the output of P1, comma, the view of simulator. Okay. As I said, you can also consider output of simulator if it is easier to understand. Is this clear? Any questions? Just to emphasize this point, so I'm only considering corruption of P2 and for simplicity, can the adversary can actually corrupt. And if, as I said, if this is confusing, let me just write out. Okay. It's clear, so let me move on. So let's go back to the main goal of this presentation, which is to construct malicious MPC from semi-honest MPC, right? And so in order to do that, we are going to use additional tools, and let me introduce the tools now. And these are the tools that you guys are already familiar with from previous classes. Tools, which is I'm going to use commitments. We're going to use zero knowledge proofs. And I'm also going to use a coin flipping protocol. And in fact, I need what is called augmented coin flipping protocol. I'm going to, if you guys aren't familiar with this, I will talk about this later. Okay, so these are the tools used these are the tools that are going to be used in the transformation. But before I actually give you the construction, let's try to get some intuition as to why these tools are even necessary. Okay. So as I said, we are starting with this semi-honest MPC protocol, right? And we have to get malicious security, right? So recall we have these three different things that the adversary can do here, and these are the things the adversary can do here, right? So we want to, in order to handle malicious adversaries, we want to make sure that the adversary cannot change his inputs and randomness at any time, right? Because that's how a semi-honest adversary works. And similarly, we want to make sure that he doesn't deviate from the protocol, right? And we want to make sure that he doesn't abort at any point of time. Oh, actually, sorry. He can actually abort at any point of the protocol, and that we cannot ensure. Okay, but that's fine. Okay, so that's not going to be an issue in this case. Okay, so yeah. So do you guys have any ideas as to what tools we are going to use to prevent the adversary from changing his inputs and randomness? Good. So we are going to use commitments. That's it, or is there anything more? So recall that in a semi-honest MPC protocol, the adversary uses the randomness given by the environment, right? And this randomness is uniformly picked. And what if the adversary in this case chooses the randomness in an adversarial manner? What if it so happens that there is one random string for which this semi-honest protocol completely breaks down? And we want to handle such adversaries, right? And to make sure the randomness is going to use in the protocol is picked uniformly at random, we're going to use a coin flipping protocol. Okay, so is the commitments part clear? So what is the use of commitment? So once you commit to a string, the security of commitments ensures that you have to abide by the string. You have to use this string throughout the protocol. Okay? So that's what commitments are useful for, and that's why we're going to use this. Okay, so what tool are we going to ensure this? Wait, there's only one thing remaining, so you have to use that, right? So we're going to use zero knowledge proofs to ensure this part. As I said, this we're going to give up. I mean, there's nothing we can do about it. So. Okay, so let's see how to go from semi-honest to malicious security using these tools. So let me give you a construction template. So before I give you the template, does any one of you want to take a stab at how to achieve this using these tools? Any ideas how to start? Okay, so we want to do secure computation of a functionality, right? So let's start with the semi-honest protocol. Okay, so we're going to have the parties. Okay, just to execute a semi-honest MPC. Right? Oh, actually, I need to prepare myself. It will be later clear why I'm using this box. So using semi-honest MPC at least handles security against these adversaries. We can only do this. So we need additional tools to handle those 3 points. So, okay, so any ideas what should be the first round in the protocol? So recall, the main problem with malicious security was that he can change his inputs and randomness at any time. And we want to prevent that. Like, we want him to not change his inputs at any point of time. Do you have a question?
Well, I'm saying that the first thing we should probably do is commit those.
Yes, exactly. Yeah. So the first idea would be to commit inputs and randomness, right? This is not going to work, so don't write it down. And then we need to ensure that somehow using zero knowledge proofs that he abides by these inputs and randomness throughout the protocol, right? This doesn't quite work. Why? Yeah.
The adversary gets the randomness that honest parties are using.
Sorry, what? The adversary?
So, if we use the coin flipping protocol, the adversary also gets the random bits other parties are using.
No, that's why, okay, that's a very good point. That's why I'm going to use an augmented coin flipping protocol. Okay, so let me take a step back. Yeah, I thought you guys were familiar with augmented coin flipping protocol, but let's just revisit this notion. So in a coin flipping protocol, let's say there are 2 parties, right? There is Alice and Bob, right? And they exchange some messages, and then both of them output the same random bit, right? And this is sort of bad for our case because we want to use a coin flipping protocol to determine the randomness of every party. And you don't want to share your randomness with other parties, right? So what you have is an augmented conflicting protocol where Alice gets the randomness, correct? But Bob doesn't get the randomness. He gets only a commitment of randomness. Okay. So this ensures that only one party gets the randomness. But that also brings us to an important point here. Just committing to randomness here doesn't suffice, right? Because again, the adversary can pick a random string that can essentially break the semi-honest protocol. So we want the randomness to be first picked via the coin flipping protocol, right? And this coin flipping protocol essentially already commits to the randomness. So you do coin flipping protocol. Okay, just to determine the randomness. So P1 has x1, right? So at the end of the coin flipping, augmented. Yeah. So P1 has x1. So at the end of this augmented coin flipping protocol, so all the rest of the parties here get commitment to his randomness, commitment to R1. He gets R1 in the clear. And all the other parties get commitments to R1. Okay, so somewhere we also have to bring in zero knowledge, right? And why is that necessary? As we discussed, this is necessary to ensure that he doesn't deviate from the protocol. And where do we use zero knowledge proofs? Do we first make the parties execute the semi-honest MPC and then use zero knowledge proofs? Would that work? Okay, why not? You know what, let's just try it out, right? Let's have the zero knowledge to be in the end, right? Can everyone in the back see this? Okay. So what is going on here is initially you commit the inputs, then you run the augmented conflicting protocol, and then you're going to use the inputs and randomness to execute the semi-honest MPC, and then you need to prove to the other parties that you have behaved correctly, right? According to the semi-honest protocol. And that you're going to prove using zero knowledge proofs. Right? Does it work or doesn't it? Right? Any ideas? Okay. So, what if the adversary cheats in the semi-honest protocol? Right? The semi-honest protocol is not just one round, right? It runs in many rounds. Yet every party has to exchange multiple messages. What if the adversary cheats in the second or third message, and potentially he could obtain the inputs of the honest parties at that stage itself, right? He gets the inputs of the honest parties and he aborts. Right? And this violates malicious security. Why? Because the simulator has no way of obtaining the honest parties inputs. Right? So what is happening in this case is the adversary here gets some honest parties inputs, and the simulator has no way of getting honest parties inputs. You can only make one query to the trusted party, right? And from the output of the function, maybe you cannot recover x1. So this is clearly not indistinguishable. This is clearly distinguishable. Okay? Yeah.
Yeah, I wanted to say maybe how to fix that, but
Oh yeah, go on.
so every time I send something to a different party, I also execute a zero knowledge probe that
Exactly.
according to
That's
my-
excellent. So the way to fix this problem is not to wait too late before you give the zero knowledge proof, but instead whenever you execute a single, whenever you send a single message on the semi-honest MPC protocol, you prove to everyone else that you have behaved honestly. Okay, so this is not separate. In fact, we'll run a single module where we do both the semi-honest MPC protocol and zero knowledge proof system. Okay, is the template clear? I'm going to explain the construction, but at least I just want to know whether it's a high-level idea. Maybe should I risk? Okay, so the goal is clear, right? So go to risk. So here's the construction. Okay. So for simplicity, let's say there are n is equal to 2. Otherwise, it's difficult for me to describe. But this can be generalized to multiple parties very easily. So you have T1 who has x1, you have T2 who has x2. They have a function f that they want to execute. Okay. So the first thing each party does is commit. Right? So this guy says commit. So I should have mentioned this earlier. COMM means commitment to something. And this guy says commits to the string. I should have thought this through. They have very little space. So I mean, I'm going to squeeze this a little bit. So X2. And then they're going to execute a coin flipping protocol. They have to execute two coin flipping protocols, right? Because one for the randomness of the first party, another for randomness of the second party. So augmented coin flipping to get R2, he gets commitment to R2. Okay, so you have augmented coin flipping for to get R1, he gets commitment of R1. Right. So and then what you do is you start executing the semi-honest MPC protocol. Right? So here it is to PC. So okay. So you execute. You send the first message. Of semi-honest MPC. And then you prove using ZK that you have behaved correctly. And you can actually use a zero-knowledge protocol because proving correct behavior of a party can be expressed as an NP relation. So why? So that every party is supposed to execute an algorithm, the next message function, right? On some input, it gets some output. Right? What does deviating from a protocol mean? Instead of using this algorithm A, it uses some other algorithm B. Right? So it needs to prove that it's using this algorithm A on this input to get this output. And this can be expressed as an NP relation. Right? So the instance itself is A, right? And the input is the witness, right? And the party can see the output. The output is nothing but the first message. Similarly, you can do this. So then this guy sends the second message. Maybe I'll continue. Second message. So, yeah. So when I write it this way, I mean P2 is the prover and P1 is the verifier. Does it make sense?
Can you explain again why zero knowledge proves correct behavior?
Oh, okay, good. So the semi-honest protocol essentially can be written down as a set of instructions, right? So the P1 on input X1 is supposed to do some additions, pick some randomness, and etc., and then it needs to send some message to the second part. So this is usually expressed as a next message function. So what the next message function does is it receives some state. Initially, this state is just the input, right? This is the initial state, right? And it also receives some randomness, and it outputs some message. Right? In this case, it's 16%. Right? So, what is the language here, right? So, the language here consists of first message. Okay, and what is the witness? The witness is just the state. Oh, I should write it as a relation and not a language. Okay, so this is the instance. This is the witness. And why is it NP? Because there is a polynomial time verification algorithm, right? That on input, instance and witness can check whether this belongs to this relation or not. So, and what is the algorithm? The algorithm is this first message function, right? So, essentially, the verification circuit essentially checks if the first message function or the next message function on input state output the first message. Does that make sense? Yeah.
Do you also check that it matches the commitment as part of this?
Good. So yes. So this check is also necessary. In fact, there are many checks that are necessary just to make sure that the randomness he has used here is the same as what he has committed as part of the augmented computation protocol. So even for that zero knowledge protocol, zero knowledge proof system necessary. Yeah. But all this is essentially proving correct behavior of a party. So let me just write down what correct behavior means. Correct behavior means that he has executed the semi-honest MPC protocol correctly. I'll just say, executing semi-honest protocol already means that he is following the instructions of the protocol, and his messages, his or her messages are computed as a function of his input and randomness that he committed here. Okay. Any questions? Yeah.
So to clarify, the instance should then include the commitments and stuff, because otherwise
Yeah.
then it just says computed from some state.
So
rather than
here,
the state.
good. So actually there are two relations. This relation is still there, right? You need, this is for the first part, right? So there's another relation which, let me call this R1. So R2 has corresponds to the commitment of X, right, comma R. This corresponds to the instance. And what is the witness?
Just X1 and R.
The state. That's how you ensure consistency, right? Whatever state is here, the state and randomness here, needs to be the same as what was committed here. Right? The state has actually more information than input and randomness, but as a substring you have X and R as part of that. Okay, and both languages are in NP. Right? Is this clear? Any questions? Okay. Okay. If there are no questions, let's look at the proof of security. Let me sketch the proof of security. Actually, even before proving that this protocol is secure, is it clear that this protocol satisfies completeness? Okay, can someone tell me why? Why is this protocol complete? Why will the parties get the output if everyone behaved honestly? Yeah.
The original protocol is complete, and all the zero knowledge protocols are also complete. So
Exactly. So the completeness of this protocol follows from the completeness of the zero knowledge protocol and the semi-honest MPC protocol. You also need some notion of augmented, completeness from the augmented computing protocol as well, right? Like, what if the protocol says that even if you behaved honestly, you don't get out? Right? So you need to define a completeness property for the concept. So the completeness properties of all these cryptographic primitives implies the completeness for the maliciously secure MPC protocol. Okay, so let's talk about proof of security, and so how do we go about proving this, the security of this protocol? Any ideas? what sort of a proof technique do we use to prove the security of this protocol? Yes, ultimately we want to construct a simulator, but to go from the real world to the ideal world, right? How do we do that? Do we just go in one step, or we go in? So we need to switch from the real world to the ideal world step by step, right? And this is called the hybrid argument. Right? So, as you pointed out, let me first describe the simulator, and then we will use the hybrid argument to go from the real world. We will see that you would need an extra property from the proof system to make the proof work, but that's not very important right now, so we will deal with it as we go on. So, any ideas how to construct the simulator? So, he has to, he has Oracle access to all these adversarial parties, right? So according to the adversarial parties, he's like an honest party, right? So he has to behave according to the protocol. So any ideas what he needs to do? And just to recall the picture, right? There's a simulator has Oracle access to U2, to Cn, all of them are corrupted. Right? And there is a trusted party. So, SIM has to somehow emulate the honest parties with respect to these parties, right? Because if it doesn't, then the adversarial parties can refuse to talk to him. Right? So, he has to emulate the behavior of P1 here. Okay, so what is the first thing the simulator needs to do here? See the protocol. So what do the honest parties do? Okay. As I said, the simulator has to behave like an honest party, right? So the very first thing an honest party does is send a commitment, right? And so he needs to do the same thing here. Commit. The question is to what? Right? What does he commit to? Like, in this case, if P1, who is the honest party, commits to X1, but the simulator does not have X1, so what does he commit to? Any ideas? Yeah.
Commit to something arbitrary.
Yeah.
Because the semi-honest protocol would not be able to tell what your initial data was, so it should be.
Excellent. Arbitrary is too complicated. Let's just stick to 0, right? So he just commits to 0. That's so just commit to 0. And it doesn't matter. And we will see in the hybrid argument why this is okay. But intuitively, is this clear? Why committing to 0 is fine? So what do commitments give us? I mean, it says that if you commit to X1 or you commit to 0, the adversary will not be able to distinguish, right? So, and as I said, according to P2 to Pn, they're actually talking to P1 and not the simulator. The simulator has to fake to these adversarial parties that he is actually P1. So he's going to crucially use the hiding property of commitments to do this. So he will commit to 0. So what is the next step? Right, so this is what he will do. So let me note it as bullets. So he will send 0 to everyone. If it was not clear, these are cons. Okay, so so now he has to simulate the augmented coin flipping protocol. Right? So Okay. And for this, he uses the simulator. What do I mean by this? This means that he is going to use a simulator of coin flipping protocol. Okay. Okay. So what is the next step? So you can see this picture, right? So once the commitments are done, the coin flipping protocols are computed, and next he has to send the first message of the semi-honest MPC protocol. Right? So how is he going to do that? Recall, it could be the case that the semi-honest MPC protocol, the first message depends on x1, right? And he doesn't know x1. So what is he going to do? How is he going to generate the messages of the semi-honest protocol? Well, again, simulate, right? So you just use the simulator of the So what about the zero knowledge protocol? We need to use something for this as well, right? So how is he going to generate the messages of the zero knowledge protocol? You see the pattern here, right? So we are simulating these protocols, so why not simulating the zero knowledge protocol? So we'll just simulate. Again, here we'll use simulator of if you cannot make out what this is, please feel free to ask me. This means simulator of zero knowledge. Okay. Okay. So is the simulator clear? I mean, this is a sketch, but you can actually write a more formal description of simulator. It will become very tedious, so I'm avoiding that. But if you want to know more details, please feel free to ask me. Okay, any questions? Yes.
And because we're doing like the multi-party computation protocol sort of at the same time as zero knowledge, we'll have to like feed messages from like the simulator of the multi-party computation into the simulator.
Exactly.
Yeah.
Exactly. That's a great point. So the question is, suppose let's say we have this simulator, right? That's, let's say, talking to P2, right? So he has generated a simulated message of the semi-honest MPC protocol, right? And he's proving something in zero knowledge, right? And even this he's simulating. So he's actually feeding the simulated message of the MPC protocol into this. He's going to use it as an instance for the simulated zero knowledge case as well. Okay? Okay. Okay, great. This is clear. So we need to show now that that the real world is indistinguishable from ideal world, right? And this we will do by hybrid algorithm. That's the only thing we know. So let's just use that. Okay, so So what will be the first hybrid? Is everyone comfortable with hybrid argument? So, yeah. Okay, so the first hybrid will correspond to the real world. Right? So the output distribution of this hybrid is identical to the output distribution of the real world. So let me just write this output distribution so what is the second hybrid going to be? So note that this is what we want to, so initially you had P1, right? And P1 has to be modified step by step to get this simulator. And once you show that, once you show the fact that P2 to Pn does not know whether he's talking to P1 or whether he's talking to simulator, we're done. Okay? Okay? We're mostly done because we also need to ensure that the simulator can extract x2 to xn. That we will deal later on. Okay? Is this clear? Okay, good. So what is the next step going to be? Yeah.
You turn one of the things into the simulator that we're making.
Good. So we will just simulate one of these protocols, right? So here, this guy, the honest P1 was running all these protocols correctly, right? So we want to make sure that ultimately we convert P1 to simulator, and we will just switch one of these protocols into a simulated one. Okay. Does it really matter which one we start off with? Okay, so let's just take a concrete example. What happens if we simulate this person? Will anything go wrong? I claim something goes wrong. Okay, so let's just take a step back. So P1 is essentially proving that he has behaved honestly, right? So that whatever he's doing is according to what the protocol should be, right? But if you start using the simulator of the coin flipping protocols or some other protocol, then the zero knowledge protocol will prevent the first party from doing that, right? The zero knowledge protocol, the soundness of the zero knowledge protocol essentially says that no, you cannot use a no instance and convince the verifier with non-negligible probability. So the soundness of zero knowledge prevents me from actually invoking the simulator of the coin flipping protocols and the semantic protocol. Right? So what do we do? So we can't invoke the simulator of coin flipping and semi-honest because zero knowledge is preventing us from doing that. So we'll simulate zero knowledge first, right? So we will make sure we will use the simulator of the zero knowledge, and then we will simulate the other things. Okay, so okay. So these are going to be the main hybrids, but as I said, there will be this issue of sending inputs to a trusted party. So I'm going to come back and modify these hybrids slightly, but for now let me present the template. Okay, as I said, we need to simulate zero knowledge. What is the next step? So I mean, can we invoke the security of semi-honest MPC protocol first? No, right? Because it could be the case that the adversary is actually cheating in the coin flipping protocol, and if he's cheating in the coin flipping protocol, it's going to affect the security of semi-honest protocol. So we will simulate that. Okay. What is the last hybrid? There's only one thing that is, we are one step away from the simulator, right? Which is the fact that we haven't simulated the semi. So we'll just simulate. Okay. And the indistinguishability of, oh, I made a huge mistake. I should have switched to commitment of 0 in the beginning, right? So there's always ways to fix it, which is define hybrid 1.5. So, okay, right? So, oh, sorry, this is not correct. It's hybrid 2.5. Oh, so it's not it's hybrid. Okay, I was doing it correctly. Okay. Okay, so can anyone see what would go wrong if you commit to 0 in 10 steps earlier? Let's say what would go wrong if I actually committed to 0 here? Exactly. So what would go wrong is if you actually commit to 0, but if P1 commits to 0 here, what is happening here is this P1 is going to use X1, right? And if the simulator uses 0, right? So then the view, right? We gave some the formal definition somewhere. Okay. Oh yeah, this view. Good. So here the view of sim would now be the output of the function where the first party's input is 0, right? But here the output of the adversary would be the output of the function with the first party's input as x1. Does that make sense? So this will have, among many things, also f of x1 comma dot dot dot, right? But this will have f of 0 comma dot dot dot. Right? So clearly the system is gone.
Should 3 and 4 be switched for the same reason? does it not matter? Does
No,
it
yeah, the
randomness?
coin flipping protocol doesn't affect the output of the protocol, right? Oh. Does this make sense? This is why you can't commit to 0 early on, right? It has to be the case that you simulate the semi-honest MPC protocol first and then commit to 0, right? Because at this point, you are essentially forcing the outputs of P2 to Pn to be a function of the first party's input. Is this template clear? So I missed an important detail, which is that the simulator has to send x2 to xn, right? So where is he getting this from? And why is this necessary? Because how else will he get the output of the function on x1 to xn? The only way he can do is to extract the inputs of the parties, right? Whatever these parties have committed, right? And then send it to the trusted party, right? And even the first party is going to send x1, and it's going to get output of f on x1 through xn. So, and how do you achieve this extraction? Is this clear? Is the problem clear? You have, yeah, go on.
Is the zero knowledge, proof of knowledge?
Brilliant. So the way to fix it is to use zero knowledge proof of knowledge, right? And so I'm just going to add these two words, and somehow magically the problem is solved. Everything else remains the same. The protocol remains the same. The construction remains the same. This only matters in the proof. Is everyone familiar with proof of knowledge? Please feel free to ask me if you're not. So what does proof of knowledge give us? It says that for every prover, for every adversarial prover, who can convince the verifier with overwhelming probability or some non-negligible probability, there exists an extractor who can extract a witness from the prover. So as you can see, this is stronger than the traditional notion of soundness for zero knowledge. So here itself, what you can do is plus extract. Okay, so and what are these x2 to x1? xn is it's what the adversarial party is committed to in the very first round. Okay, is this clear? So once this party extracts, is going to send this to the trusted party. He's going to get the function, its output, and actually he's going to use this output to simulate the semi-honest MPC protocol. Recall that the simulator of the semi-honest MPC protocol receives as input the output of the functionality. Right? So it's going to use using f of clear? Any questions about the proof? So now that the protocol I gave for the case when n is equal to 2, because it was hard for me to describe, but the proof is for n parties. Right? So is it clear how to go from 2 parties to n parties for arbitrary n? It's the same thing. The only important thing I want to point out here is you execute these protocols sequentially. So meaning that party P1 will send the first message, then he will prove in zero knowledge. All the other parties will look at this zero knowledge proofs, right? It will wait and verify, and then decide to send their messages. So all of this happens sequentially. You can hope to parallelize. So maybe the other parties don't wait for this zero knowledge proof to complete. Maybe they actually send the second message of the protocol while they're receiving the zero knowledge proof messages. This leads to complicated issues, and there have been several years of research to sort of handle such kind of issues. They usually come in the area of non-malleability, so I'm not going to discuss this in this lecture. But if you're more interested, I'm happy to talk about it afterwards. there are no more questions, we are done. I'll stick around for a while if you want to